In the elegant and abstract realm of classical mechanics, there exists a profound and powerful discipline known as Lagrangian mechanics, a formulation that transcends traditional Newtonian mechanics and provides a mathematical framework to describe the dynamics of mechanical systems with unmatched elegance. This narrative, woven with principles from variational calculus, analytical mechanics, and differential geometry, unveils the symphony of generalized coordinates, kinetic and potential energies, and the Lagrangian function that guides the celestial dance of particles and systems. Principle of least action. At the core of Lagrangian mechanics lies the principle of least action, a fundamental concept that asserts nature follows a path of least action. This principle, articulated by Pierre-Louis Maupertuis and further developed by Euler and Lagrange, becomes the guiding light in Lagrangian mechanics, suggesting that the true path of a system is the one that minimizes the action integral. Generalized coordinates and velocities. The discipline unfolds its mathematical elegance by introducing generalized coordinates, configurational parameters that describe the configuration of a system beyond the traditional Cartesian coordinates. Associated with these coordinates are generalized velocities, providing a nuanced description of the rates of change in the system's configuration. Lagrangian function. Lagrangian mechanics introduces the Lagrangian function, a mathematical entity defined as the difference between the kinetic and potential energies of a system. This function becomes the central character in the Lagrangian formulation, encapsulating the dynamics of a mechanical system in a concise and powerful form. Lagrangian equations of motion. The narrative deepens with the derivation of Lagrange's equations of motion, a set of second-order differential equations that govern the evolution of generalized coordinates. These equations, derived from the principle of least action, elegantly express the dynamic behavior of particles and systems, transcending the need for force considerations. Conservation laws and symmetries. Lagrangian mechanics becomes a vessel for the exploration of conservation laws and symmetries. Noether's theorem, a profound contribution to the field, establishes a connection between symmetries in the Lagrangian and the emergence of conserved quantities, offering deep insights into the underlying structure of physical systems. Hamiltonian formalism. In the dance of mathematical transformations, Lagrangian mechanics seamlessly transitions into the Hamiltonian formalism. The Legendre transformation converts the Lagrangian into the Hamiltonian, introducing conjugate momenta as new protagonists in the dynamic narrative of mechanics. Action angle variables and integrability. Lagrangian mechanics extends its reach to the celestial ballet of integrable systems. The discipline explores action angle variables, a set of coordinates that simplifies the description of systems with multiple degrees of freedom, paving the way for the understanding of integrability in classical mechanics. Applications in celestial mechanics. In the Cosmic Odyssey, Lagrangian mechanics finds application in celestial mechanics. The formulation becomes a powerful tool for analyzing the motion of planets, moons, and celestial bodies, offering a comprehensive understanding of the gravitational ballet that governs our cosmic neighborhood. Relativistic Lagrangian mechanics. In the relativistic realm, Lagrangian mechanics adapts gracefully to the principles of Einstein's theory of relativity. The Lagrangian formulation becomes a versatile framework for describing the dynamics of particles moving at speeds approaching the speed of light, bridging the classical and modern frontiers of physics. Quantum mechanics connection. Lagrangian mechanics forms a bridge to quantum mechanics. In the quantum world, the path integral formulation, inspired by the principle of least action, becomes a cornerstone, connecting the classical elegance of Lagrangian mechanics to the probabilistic description of particle motion in quantum theory. In essence, Lagrangian mechanics is the poetic symphony that transcends the traditional language of forces and accelerations. It is the discipline that, through the language of generalized coordinates and variational principles, unveils the inherent elegance and simplicity underlying the complexities of mechanical systems. In the grand theater of classical mechanics, Lagrangian mechanics stands as the virtuoso, composing the mathematical sonnet that guides the motion of particles and systems through the rich landscape of configuration space.